Okay. Okay, again. Shh. Too much crosstalk. Deny, for example. Okay.
I'm just putting it in my pockets.
Okay. Covalent bonds. That is where you need to get your head around. That is year 10. And that is the bond we're dealing with. Okay? When non-metals come together to share electrons. No electrons are transferred. Instead, atoms share their outer shell electrons to give each other a noble gas configuration. Very quickly, on your periodic table, what group is carbon in?
4.
Carbon is in group 4. How many valence electrons does carbon have?
4.
4. So, this carbon has 4. Now, if the carbon has 4, but it wants 8 in its outer shell,
Take all share.
then it can neither gain electrons from stealing, nor can it lose electrons. So what it will do, if it has 4 electrons, then it needs to share all 4 of those in order to get 4 shared with it. Okay, it wants to gain 4 electrons, so it shares 4 electrons. And what it's doing here is, here's hydrogen. Hydrogen is in group 1. It has 1 valence electron. It wants to, in this case, share 1 to gain 1. So this hydrogen shares an electron, and that little cross electron goes around the carbon, around the hydrogen, around the carbon, around the hydrogen. So sometimes, when each of these do that, sometimes that carbon has 8 electrons in its valence shell. And sometimes this hydrogen has 2 electrons, and sometimes this hydrogen has 2. And so what you see there is the crying baby has the situation covered where you have a valence electron count of a noble gas, 8 for carbon and 2 for hydrogen, and electrically neutral. So that's why you have covalent bond. But very importantly, it's a non-metal bond. Now, what group is oxygen in? 6. So how many valence electrons does oxygen have? 6. There you go. 1, 2, 3, 4, 5, 6. Oxygen wants to gain 2. So how many must it share? 2. You're right. If it wants to gain 2, it will share 2. Hydrogen, hey, look at this. Hydrogen, 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 popping up quite a bit. Hydrogen acting like a non-metal. Yes, Lucas?
So why doesn't it just take...
Because
Sorry, no, wrong. No.
these are non-metals and they hang on to their valence electrons. Did you watch the video from last class?
Yeah, I was here last class.
Okay.
But I was
So,
why doesn't it just go to group 2 again?
yeah, these are the non-metals in the top right corner that don't lose electrons, and if the only thing around them is other non-metals, they can't steal electrons from things that are also holding onto their electrons strongly, and so they share. So oxygen here sharing 1 to gain 1, sharing 1 to gain 1. So oxygen wants 2, it wants to gain 2, so it shares 2. Hydrogen wants to gain 1, so it shares 1. And you get this H2O configuration. Water. Nitrogen. What group is nitrogen in? 5. It wants to, and how many does it want? 8. The answer is always 8. It wants a total of 8. So it wants to gain 3, so how many will it share? 3. So there's nitrogen, 2 there, 1 there, 1 there, 1 there, and hydrogen again sharing 1 to gain 1, and so you get ammonia. Okay? So, now on your periodic table, note the trends in covalent bondings for groups. Have a look at your periodic table. If you're in group 5, okay, we've got in group 5 nitrogen. Nitrogen has 5 valence electrons. How many does it want to gain? 3. It wants to gain 3, so it shares 3. Underneath hydrogen, you have phosphorus in group 5. How many electrons does phosphorus want to gain? 3. So how many will it share? 3. What about arsenic? Also in group 5. Are you seeing a pattern here? It's in group 5, it has 5 valence electrons, it wants to gain 3, so it shares 3. So you will see similar reactions as you go down groups, which should not surprise you. You know in the periodic table that as you go down, that the members of a group have similar reactions, but as you go down the group, they become more violent, or more active. Now, let's see. Covalent molecules tend to be discrete. You need that point. Discrete means they form standalone molecules. No crystal lattice here. Huh? A covalent bond is sharing electrons. Huh? They share electrons, yes.
With arsenic, is that a non-metal?
Yes. Actually, arsenic is... Sorry, that was a bad example.
Yeah.
Arsenic's out of the jigger. It would be much better to use oxygen, sulfur, and selenium. Yeah, exactly. Not a great example. I wasn't... Yeah. But... Yeah. But, yeah, these are the non-metals in that little staggered formation in the periodic table. Now, you need to understand that point. They form discrete molecules. They don't form, you don't get water crystals like you do salt at room temperature. Okay? Well, that's different. That's because they've been robbed of atomic energy, thermal energy. Now, okay, there you go. Draw out these covalent compounds, then draw the bonds between the atoms. Okay? So, I'll do the first one with you. What group is hydrogen in? 1. So, it has 1 valence electron, and this hydrogen has 1 valence electron, and there's your covalent bond. It has 1, so it shares 1. It has 1, so it shares 1. What about oxygen? What group is oxygen in? 6. So it wants to gain 2, so how many does it share? 2. So you have to draw all of the electrons. 1, 2, 3, 4, 5, 6. Actually, I'm going to put that up there. And 1, 2, 3, 4, 5, 6. So each oxygen is sharing 2 along the boundary, and so it has, on occasion, a total of 8. Yes?
If they're always ending up with the same amount of electrons at the end, why do they bond?
They're sharing the electrons. The electrons are...
Yeah, but why do they bond and share? It's just...
What are the 2 things atoms want?
8 electrons, right, yeah, gotcha.
It's like... Okay, your question, I understand the question you're making, like, why do molecules form? Yeah? It's why does this pen fall? And you say, well, gravity. Yeah, sure, that's very true. And it's a fundamental aspect of the universe, gravitational attraction between bodies with mass, yeah? You'd be surprised if I dropped the pen and it didn't fall. Yeah? This is atoms falling, if you like.
Yeah.
It's a fundamental property of this universe that molecules form because of this drive, if you like, for atoms to be electrically neutral, but to have 8 electrons in the valence shell. Yeah? And so, they do this. Yeah? So, that's an interesting question. So, guys, fill in those. I will give you a few minutes to have a go at those. Yes. Well, you don't have to draw circles, just use symbols. Actually, no, just hold off for a moment. Just hold off. Just hold off. What I'll do, rather than pause on that activity, I'll push through, finish this part of the slideshow, and then we'll do that activity. because otherwise you'll end up with dead space on that video. So, don't worry, we'll come back to that. Now, have a look at this. Okay, so what are the differences between ionic and covalent bonds? Okay, ionic bonds are non-metal and a metal. They transfer electrons. They have a positive and a negative charge. Don't worry about the naming. You will never be asked about that. You can be asked about that. Typically solid at room temperature. High melting and boiling points. High attraction between particles. It's a strong bond. Yes? Now, so just knock that one out. Oh, sorry, not that one. That one.
The history question again.
Yeah.
Okay. Covalent compounds. A non-metal. They share electrons. There are no electric charges. They can be solid, liquid or gas at room temperature. They have low melting and boiling points, and there's a weak attraction between molecules. You need to understand those key properties, the differences between a covalent bond and an ionic bond. What is it, and the types of molecules that they form. I'll give you a couple of minutes to take that down. Yes, Drew. Drew's going to say.
I do. I get that table.
So it's easier. You can't steal electrons. You share them.
Can't be enjoyed.
Yeah, I was going to say.
It's only non-metal.
And it can be with any non-metal you want.
Yeah.
Alright.
And so you get three types of atoms combined together. Yeah. Don't hang up. Ooh. Hey, don't hang up.
Pull your head in, mate.
Yes.
What's the difference between a polyatomic ion and a covalent bond?
Like Daniel Martin Key.
A polyatomic ion is an ion that is made up of non-metals. They are covalently bonded.
Daddy's middle way.
But it has a charge. So it will stick to a metal. Yes.
Are we right on the list here?
Yes.
So I was going to take a photo.
Don't hang out. I'm changing that in a moment.
That's why I was going to take a photo of it with my phone.
No, do the work now.
You can watch the video, Danny, there's going to be a slideshow video. Here it is.
You were currently in that video.
Probably why you get 50 views.
I'm only going to give you a moment, a minute more.
Heading.
I'm learning how to type.
Unless you can remember it from last year. You do need to know these different properties.
No charges. Oh, next year. Mr. Mansfield, I just gotta take a photo of this and write it down. Just because I don't think that I'm not.
You can.
What's the video? No, I'm just gonna go with this and jot it down. Well, you have $1.50 bucks. That got nothing in it. Do you want me to take a
You've
photo?
got about 60 seconds more.
Okay, room temperature's just going on.
What do you think 60 seconds is? Wait, let me take a photo. Got it? Oh, wait, no. Guys, wanna go on the chin? Wait, there's an hand. shell that I did not get. One.
So when you start counting the figure, when you get past these three,
What do you mean?
yeah,
These
numbers
ones.
don't change.
It's because we skipped these ones here. Because they're just
Okay, let's move on. Now, okay. Now, oh, I've frozen that screen. Just unfreeze. Right. Bohr diagrams. Now, a Bohr diagram you're not going to use this year, but you need to know what they are. Bohr diagrams show the distribution of electrons among different shells. Okay? So, here is carbon. What group is carbon in?
Four.
Again, everyone, have a look at your periodic table. What group is carbon in?
Four.
But what's its atomic number? 6. So it has a total of 6 electrons. But in chemistry, I said this to you before, where in terms of chemical reactions, which electrons are important?
Valence.
Did everyone hear that? It's the valence electrons. So the Bohr diagram with all 6 electrons, 2 in the K shell, 4 in the L shell, not really useful for us at the year 10 level, but you need to know what they are. Now, electron configuration is a numeric representation of the distribution of electrons in an atom or molecule. So there's carbon, 2, 4. 2 electrons in the K shell, 4 in the L shell. So if you see the term, and that's on your sheet already, and sometimes it says EC on your revision sheet for electron configuration, and that one is a short way of writing down, effectively where the electrons are. But again, we won't be using Bohr diagrams, but you do need to be able to read them, you do need to be able to understand them, but that is very much year 9. Okay. Now, can I change? Yep.
We don't need to write it down.
You need to know what they are. You need to know how to navigate through them. Right. You will be using these. Lewis structures. Okay. Or Lewis dot diagrams. 2 different names, same thing. Diagrams that show covalent bonding between atoms of a molecule and the lone pairs. We'll talk about this, but you'll notice on my diagram, I always, if I've got, say, 5 electrons, and I'm going to share 3, there's 2 left over, and they stay as a pair. Now, lone pairs are defined here. Non-bonding pairs of electrons must be shown in all diagrams, double asterisk, because I'm telling you, point blank in the exam, every time you don't show a lone pair, you will lose half a mark.
What's a lone pair? How do you show it?
Lone pairs are non-bonding pairs. Here's nitrogen. There's nitrogen, group 5. Lone pair. Hydrogen, hydrogen, hydrogen. There's ammonia. There's the lone pair. If I draw that in the exam and I leave the lone pair off, that's half a mark every time. You have to put the lone pairs in. You show all of the valence electrons. So, listen up. A Lewis dot diagram is showing dots. Here is lithium. What group is lithium in?
Group 1.
Group 1. It has how many valence electrons? 1. What group is carbon in? 4. It has 4 valence electrons. Very easy to draw single atoms. Now, oxygen is in group 6. It has 6 valence. Oh, don't do it that way. It has 6 valence electrons, and it wants to share 2 to get 2. And hydrogen wants to share 1 to get 1, and that is what the Lewis dot looks like for water. Okay, it's showing the shared electrons. Okay, now, lastly, the octet you to write that down on your periodic table beside the noble gases. The octet rule, atoms combine to form molecules that generally lose, gain or share electrons until they attain or share 8. And that's how you get a noble gas configuration. That's one of the two things that the crying baby wants. A noble gas configuration, 8 electrons in the valence shell if you can get it. Okay? Share them, steal them, donate electrons if you have to, but that is the octet rule. Okay? You'll need to know all 3 of those, and all 3 of those are new.
Yeah.
Yep.
Yes.
What if you put 3 elements together to 8? What if you put 3 elements?
Yes, you can do that.
You can? What is it that?
What do you think ozone is?
I don't even know what that is. It's generally
Yeah. Okay. Now.
will share
Sorry, 5
electrons until
Okay.
they
Any other questions?
See how the hydrogen has the 2 at the top, and the 2 on the right, and on the lone pairs. Of the 2 electrons on the
Okay.
top, 2 on the right there, lone pairs.
It's like holding hands.
Yeah.
Remember, I always put crosses and dots because it makes it, there's a hydrogen one, there's a hydrogen one. And each hydrogen has 1 electron to share. It shares 1 and it gets 1. And each oxygen, the oxygen will share 2 to get 2. Yeah?
The ones
So
that have no
think of these, Danny, as going like that. Orbiting around the oxygen, around the hydrogen, around the oxygen, around the hydrogen. And that, around the oxygen, around the hydrogen. Yeah? Whereas these ones just stay around the oxygen. Yeah. So sometimes the oxygen has 8, and sometimes the hydrogen has 2. Okay. And so it's got a noble gas configuration. Now can I change?
Yes.
Okay.
Lovely man.
Lastly, now this one is Lewis dot diagrams take a lot of work, and you're lazy, I'm lazy, everyone's lazy. So we use structural diagrams. Structural diagrams, look, oxygen has how many valence electrons? 6. Oxygen has 6 valence electrons.
Oh, but 2 get shared.
Now, it shares 2 to gain 2. Hydrogen has 1 valence electron. Hydrogen shares 1 to gain 1. Each of these lines represents a pair of electrons. Understand that idea? Each of these lines represents, think of it like a bridge. This oxygen electron can cross the bridge and go around the hydrogen sometimes. This hydrogen electron can cross the bridge and go around the oxygen sometimes. Same thing here. This is the Lewis dot diagram. Those are the 2 electrons. Stretch them out, form a little bridge, and just draw a line between them. And that is a faster way of drawing diagrams. Lewis dot diagrams, you go a little mad when you have big molecules. Wait until we start doing hydrocarbons. We have C20H22, and you have to draw it.
What's the point of drawing?
Oh, not 20. It'll be C10H22. That would be a better example. That's a lot of dots. Much better to just go. So,
There's an issue is these can be shown as either.
so
Oh yeah, typo. These can be shown as either.
where is that?
First line to second line.
Diagrams. These can be shown as either.
Oh, that's a photo. Sure.
Yeah, I reckon that's pretty good.
There we go. Done. Okay. So, now I think, lastly,
But Miss Matt, how do you draw the shared line diagrams when you have, like, instead of hydrogen, you have something that has more, just draw more lines?
if you're sharing, if you're doing something like, let's do something strange like nitrogen with my lone pairs, and I'm just going to do something odd like
Yeah, okay, you just draw lines.
is that legal? Is that diagram there?
That's one, that's two.
Does that obey the rules of our game? What group is what group is nitrogen in? 5. So it's going to share 3 to gain 3.
Yep.
Sharing from the nitrogen end. What group is oxygen in? 6. It's going to share 2 to gain 2. Sharing. What group is hydrogen in? 1. Shares 1, gains 1. That is legal. Lone pairs are shown, full marks. Okay? So these are the rules of the game. It's a simple game. Okay? You can make effectively an infinite number of molecules from this, from the way these things are shuffled together. Wait till you get to hydrocarbons.
We get some practice ones of these.
Yeah, we're doing that right now. We've gone through the theory, because of that, and then we stop and we do the practice. Okay. We'll get some. We'll do some practical work with these now.